Just want to make sure it's okay to record it.
It's fine. Thank you for asking. No.
Thank you, thank
So the first thing I want to do is say thank you for coming on this tour. We are a nonprofit. We are mostly staffed by volunteers. I'd say we're about 96% volunteer staff. We are owned by the Carnegie Institute. They don't fund us. They support us in other ways, but not with money. And we are housed in the Los Angeles National Forest. So these tours are a source of income for us, and I just want to say thank you for coming with us. I like to tell the story of the mountain, the telescopes, and just kind of a general overview. So the story most clearly starts with the indigenous people. The group that probably lived up here, but not full-time, would have been the Tongva group. And I say that, sometimes known as the Gabrielinos, which is not their word, so we use Tongva. But I say that because at the bottom of red box you see Harakmanga, and in the Los Angeles area, any word that ends in NGA or NGVA was a Tongva settlement. So you've got Tahunga, Cahuenga, Topanga, and that sort of thing. From what I can find, and it's really hard to get information about the indigenous people who lived here, this would not have been a year-round residence because the winters are brutal. We might get 4 to 5 feet of snow, and it might have been a trading center. But, so those were the early people. And then we're going to fast forward to 1864. A young man named Benjamin Davis Wilson came from the East Coast to seek his fortune. The notion was he was going to get on a boat and go to China. But while he was waiting for the boat, he met and fell in love with a young woman who was the daughter of one of the original rancho owners. And they got married, and his new father-in-law really liked him, and he gave him a bunch of land. And so by that time, they were calling him Don Benito. He was well-liked. And he planted grapes, and he was going to have a vineyard, which he did. And in his travels, he kind of wandered up and discovered this peak. So it bore the name Wilson's Peak, later to become Mount Wilson. The trail up took the name of Wilson's Trail, later to become Mount Wilson Toll Road. So he came up and saw, whoa, this is nice, and there's all this free wood. I'm going to cut down a bunch of trees, make casks for my wine, and I'm good to go. Well, he did, but the wood was porous and all the wine drained out. So that's pretty much it for Benjamin Davis. Bye-bye. Next, we have in the 1870s, now that Benjamin Davis Wilson had kind of discovered this mountaintop and there was a way to get up here, the local people took it on as a getaway spot, which the mountain is still very pristine, so just erase all the buildings from your mind, and it was pretty much the same. So they kind of established a feeling of ownership, and it was a great vacation spot. And so during the 1870s and early 1880s, they were coming up here. But then in 1889 and 90, Harvard and USC decided to bring a small telescope up here, a 13-inch refractor. Now there's 2 types of telescopes. Refractors have a lens at either end of either a physical tube, which carries light, or just a beam of light, like in the 2 tall solar scopes. And reflectors use big mirrors. So reflectors are what our night scopes have. The snow in my telescope is a reflector, the 2 towers are refractors. But anyhow, they brought it up, and they immediately discovered something that is true today. We're at 5,700 feet, we're above the inversion layer, so the air is stable. And at that time, there was little to no light pollution. So astronomers refer to the viewing conditions as the seeing. The seeing was phenomenal. So they're getting great results. They built this funny shaped kind of dome, and they discovered the seeing was amazing. They're getting great results. They make big plans to have a 40-inch refractor. And keep this in your mind because it comes up later in the story. So the mirrors and lenses on big telescopes start off as glass blanks. And then if it's a mirror, they grind and polish the surface, whether they want it flat or concave or parabolic. And then in the old days, our big mirrors were coated with silver, now with aluminum. So that 40-inch glass was going to be the world's largest refracting telescope. It was a brutal winter. There were feet of snow, and pretty soon Harvard and USC are kind of getting on each other's nerves. So they thought, we're going to make it till spring. It'll be great. It'll be beautiful. Well, it was, but there were a lot of rattlesnakes, plus all the local people who had ownership of this mountain came up, and here's this funny shaped building. So they're knocking at the windows and crawling around and waking up the astronomers. So Harvard and USC had enough, they left. But in 1889 and 90, young George Ellery Hale was a student at MIT studying physics, and he was working at the Harvard Observatory. Guess what he knew about? 2 things.
Mount Wilson.
He knew about Mount Wilson, and he knew about that 40-inch blank. Years later, when Hale was 24 years old, he founded his first observatory, Yerkes, in Wisconsin, where he had his wealthy dad procure that 40-inch glass blank, and he made his first telescope out the door, what is still the world's largest refracting telescope. And this was Hale's MO. Every telescope up here was the largest in the world until he built the next largest. So that's just a little bit about Hale. Let's go. I'm tired.
When they say like a 40-inch telescope, I mean in diameter?
That is the diameter of the lens.
Of the lens.
So night scopes are named by the diameter of their primary mirror, or if it's a refractor, by the diameter of the lens. Like we have a 6-inch Brashear telescope here, that's its lens diameter.
Okay.
Okay, so we have our first view of 2 of the 5 scopes. On the left is the 150-foot solar tower. You will be going in there, but not to the top. And on the right is the 60-foot also solar tower. No longer used as a solar tower. USC has a helioseismology camera up there. They're measuring seismic activity on the sun, but that's the only one of the 5 scopes not operating in its original configuration. The Snow Solar Telescope, which we'll be going in, is a horizontal scope, and it is the founding scope. It is named after Helen Snow, who paid for it. That went up, that's founded the observatory in 1904. In 1908, Hale didn't just put up the 60-foot solar tower, he also put up the 60-inch night dome. And then in 1912, the 150-foot went up, and in 1917, the 100-inch went up. 5 telescopes in 13 years by a 36-year-old. Some of us might be older than 36, so we realize how very, very young that is. You'll hear me, I'm amazed at what went on up here 7 years down the line. I'm just as amazed, if not more, than the first day I walked in here. So what Hale did here is so unique and so amazing.
And just to get up here is a huge thing.
Exactly.
Especially in those days.
The logistics, because everything came up Mount Wilson Toll Road, which was about 8 feet wide. So the snow came up with mules and carts, and the rest came up with a big truck, but they still were told had the mules pulled.
And it was all funded by his dad?
No, his dad started him off, but then Andrew Carnegie fully funded Mount Wilson in December of 1904. When Hale was a little boy, he wanted an expensive microscope, and so Dad got it, but then next he wanted an expensive telescope, so his dad said, well, George, you have to write a proposal. So he had to say his budget, what he wanted to accomplish, describe it. This served him well later in life, so as we like to say, Hale became very adept at gently persuading people to part with massive amounts of money. So that's how this place
Good
was
trait
funded.
to have.
Yeah, for his dad first, and then Carnegie was the first big benefactor.
Oh,
Yep.
wow.
Okay. Yes, please feel free to ask questions. All right. So, if you can't hear me at the back, which is doubtful because I'm very loud, just raise your hand and I'll up the volume. But I want to take a brief stop to describe the infrastructure. So, Hale was born in 1868 in Chicago to a very wealthy father. He, from a very early age, was interested in, and most kids, and I love life science. Later on, when he was 14, he had this weird neighbor. And everybody talked about this guy and said, this guy is just strange. He goes in this funny shaped building at dusk and he comes staggering out at dawn. And well, he was a really famous astronomer. And Hale befriended him at about the age of 14, and that's when his love of astronomy began, particularly solar astronomy. So this was Mount Wilson Solar Observatory. When it was founded, the first 3 scopes are solar scopes plus the 60-inch. And then in 1918, after the 100-inch was up and proved itself for that first year, they dropped the solar from the name. But anyhow, little George was born in 1868 in Chicago, grew up interested in science and making things, had a little shop where he had his brothers and sisters work, brother and sister. And then he went to MIT as an undergrad and worked at the Harvard Observatory. When he founded Mount Wilson in August of 1904 with the SNO telescope, he was negotiating with Andrew Carnegie to fully fund it, and that happened in December of 1904. But Hale coughed up 28 grand of family money to establish an infrastructure, and that's about 800,000 now. So at the end of the mountain, you can see a building at the far end. That is called the monastery. The reason it is called a monastery is Hale was a traveler, and somewhere in his travels he went to a monastery. He really liked the idea of no women, all men with a shared passion. The first observatory he worked at, the wives and kids were there, and evidently too much drama for Hale, so forget the women. And so the first monastery burned down. The second one is still well over 100 years old, and it is a concrete building with steel shutters over the windows, so we made it through Bobcat. But that fire came about 8 feet from that building. And you'll still see charred bases of tree trunks from Bobcat. Eaton, we did fine. It stopped at the lower line. Next, so he had a place to stay. And then that small dome is called the Cook Dome. We have a modern telescope in there. And then over here, you'll see kind of scaffolding in a rooftop. That was originally the power plant with 2 incredible DC generators and batteries to store power. You can see them on the engineer's tour. So he had a place to stay, he had power, and then third, they needed water. So originally they dug a reservoir, later on wells. These are not traditional vertical wells. Somehow our water comes from between rock layers. So Hale had it all set up, and in 1905 he made his first big discovery with the snow. So we'll continue. All those burned trees, those are from the Bobcat fire.
When was the Bobcat?
Starting in September of 2020, burned until November of 2020. Yep. It was wild. It was much scarier for the mountain.
The sun became red.
It did. That firelight is creepy, isn't it? It's beautiful, but I think it's kind of eerie. Yeah, the sun did become red. Do you see the road that's just about halfway down the mountain? That was Wilson's Trail, and then it was broadened, it became Mount Wilson Toll Road. That's the road all the telescopes came up on in pieces. And when you see the scopes, particularly the 100-inch, that in itself is something to just marvel at. The towers are called Mount Harvard. Nothing to do with Harvard, but Pasadena really liked having Harvard and USC up here. And when they left, they thought, how can we get them back? So they said, let's call that Mount Harvard. Well, it didn't work, but it still bears the name Mount Harvard. And it's some kind of communications tower. So,
Is that toll road closed?
no, you can hike that road. Yeah, and many people do. It was closed after the fires, but I believe it's open again. Yep. Okay. We'll continue. So this is just signage telling you that we are owned by the Carnegie Institute and funded by our own Mount Wilson Institute. I encourage you to go to our website. There are many opportunities to look through the telescopes here. We have concerts in the 100-inch. There's one this afternoon, two actually. We have a movie matinee. There's lots to do up here. You can rent a telescope with your friends. You can get your own ticket and come to a public ticket night. There's just lots of opportunities to look through the scopes. Just a handy tip, September. The gas giants come out, Jupiter and Venus and Saturn, and that's really fun. Planets are fun, but it's great all year. All right, that's the SNO, that long horizontal telescope. We'll be going there later.
The biggest gas giant in the family is rich. They're 100%. Can go through that, except their gravity is perfect. Yeah. It's 100%. But the gravity. I'm Carl, by the way.
Oh, you're Carl, Patricia. I heard you were coming.
They told me I got the good job.
Oh. Yeah. Oh, you are? I didn't remember them.
Yeah, that's what they told me today.
What comes this from? Okay, so we're just going to stop briefly. This is the 150-foot solar tower. Went up in 1912, or went up in 1910, operational 1912. And I'm stopping here to show you the 60-foot tower had some stability issues. They did a successful retrofit, but when they built this one, you can see there's an outer structure that's supporting the dome, and then the inner structure supports the actual weight of the mirrors and the telescope. So that was a design feature that worked really well. Okay, we're gonna go in the museum and then to the 150 foot. There is so much to look at in here. I'm not going to go through every item, but I do invite you to come back and check out everything in here after the tour. There's some tremendous information. I'll point out a couple highlights. But meanwhile, this is a model of the observatory. Now, after Hale graduated from MIT, he moved back to Chicago to the family home, and his dad built him a real observatory next to the house called Kenwood. And Hale designed something called a spectroheliograph. You'll see it in the SNO. It's not operational, but you get the idea. And so he was working on that, and he'd already begun his solar work at Harvard and was continuing it at Kenwood at the family home. So one day, knocked on the door, this, at the time, young man said, "Hi, I'm Ferdinand Ellerman. Do you need help?" Well, of course. Ellerman then went with Hale to Wisconsin to found Yerkes. And then at Yerkes, Hale picked up George Ritchie, his chief designer and optician. Ritchie had an assistant named, I believe, Frederick Pease. There was a man, Walter Adams, who later took over as director. Ritchie, Pease, Adams, Hale, and Ellerman. That was the group. So they founded Yerkes, and then they came and founded Mount Wilson. But Ellerman was known as the man who could do everything, and they all wore many hats. They were all astronomers, and they were all taking photos through the telescopes. They were all opticians and mechanical, but each one had a specialty. So Ellerman was the one who was good at everything. And he was very excited to move from civilized Wisconsin to wild California. So the story is he had jodhpurs and machetes and guns and hats and all this equipment came out. and it wasn't that wild, and so he just had to take it all off and get to work. So one of the things he did in the early 20s was he built this model of the observatory. These trees and bushes are not randomly placed. They are actually where they were. And it was a cloudy day, which just cracks me up. So, this is the end of the mountain. This used to be a little solar observing station, and the story is that the solar observer built a little solar oven for his wife, and she would bake muffins and bring them to the night observers. It is now a JPL installation, and they're measuring air quality in Los Angeles using a spectrograph. So we'll talk about spectroscopy more later. This is where astrophysics started, as opposed to observational astronomy. We'll talk more about that. So let's just follow this. So here's JPL, that's off limits to us. Here's the monastery, and it's where volunteers can stay there, different groups stay there. This is called the Hooker Cottage because a man named John Hooker paid $45,000 for the mirror for the 100-inch telescope. Now our director of telescope stays there. These buildings aren't here, so here's the road. Here's cabin 9. This is my cabin, cabin 8. Cabin 7. So these are original cabins to the monastery. We don't know exact dates, but they're well over 100 years old. This is the power plant with the generators. This used to be a laboratory. Hale believed, basically from childhood, that all observatories should have a lab. Mount Wilson started with the lab, they outgrew it. It moved to Santa Barbara Street in Pasadena, which is where Carnegie is, and they still have that, a big lab. Now it's a library. This is the snow, 1904. 60 foot, 1908, 60-inch, 1908. These are reservoirs. We're right across from this, the 150-foot tower. This is a different building. This was something else. And now, of course, it's this, behind here is an auditorium where we have lectures and movies. I think this was built in 1947-ish. Okay, so then the road continues. This is a garage. I don't know what it was then. There's houses, but they were built after, there's 3 or 4 houses. They were built after this model was made. And then you go across the bridge to the 100-inch telescope. And then behind here, the Chara Exhibit Center for High Angular Resolution Astronomy. They do interferometry. It's run by Georgia State, but it's housed here. It is state-of-the-art interferometry, but curiously enough, the very first interferometry was done up here by a scientist named Albert Michelson, I think 1923. You can see that interferometer. Yes?
What's interferometry?
Thank you for asking. A very civilian explanation is, interferometry measures the angular diameter, brilliance, and surface features of stars. There's a board you can read more, and there's a whole chart exhibit. But Albert Michelson did that on top of the 100-inch in 1923. So there's all these connections with the past and the present here, which I really like. So this is the model. Over here we have springs and we have a pump house. So that is a source of water for us unless it's a drought. Otherwise we collect rainwater in the reservoirs, and then it's treated and it's safe to drink. So you can drink the water here. It might taste kind of yuck, but it's okay. Now, when you come back, you can read about the 4-inch refractor of your keys. You can read about Hale setting up. You can read about Andrew Carnegie. These photos were all taken between about 1905 and 1950. Over here, we look at a couple items. Oh, and very important, the speed of light was discovered out here by that same scientist who did the interferometer, Albert Michelson. So check that out when you come back, right? All right. Over here, this is when the telescopes are made, if we're making, it doesn't matter if it's a lens or a mirror, it starts off as a glass blank, just regular old glass, very thick. And then this is one of the grinding polishing tools. They would grind and polish the surfaces till they were just perfect. The story is that Ritchie worked on the 100-inch mirror and the 100-inch telescope, grinding and polishing it, prior to coating it with silver for up to 7 years. So it was a very painstaking process. Over here we have a bunch of correspondence from Hale and various people. Now you'll see some correspondence with Hale and a doctor, and that's because from the time Hale was a little boy, his mother had the same issues. They called it a nervous constitution. We might call it anxiety disorder, bipolar. But he suffered greatly all his life, and it manifested itself in a lot of gastrointestinal things. So there's a lot of correspondence with the doctor. Hale's health was so extreme that he stepped down as director in 1923. He was 70. No, he died when he was 70. 1923, and then Walter Adams took over. He died when he was 70, and it's a shame because these days there would have been help for him that simply wasn't available then. But Hale managed to do a tremendous amount in his life, a long time up here. Okay, so now we're going to go see the 150 foot.
So I'm going to check over time here. Yeah, just basically giving it all one over to like modernizing
Same as with everything in the auditorium. I'm not going to dwell on this because this is something you can come back if you want and revisit later. But just briefly, this is the design of this telescope. So the solar scopes have two mirrors at the top. They're called a coelostat. They're both flat surface. The bottom one tracks the top by means of, in the snow, a clock drive. Steve has something different. They replaced it. But anyhow, so you get the sun in the bottom mirror up to the top. And then he feeds his through an objective lens up here. And then there's also a lens above the spectrograph, above the diffraction grating. So by definition, this is a refracting telescope because you've got two lenses with light between. But anyhow, so the light travels 150 feet down to the slit, goes through the slit, goes another 75 feet down in the pit where his spectrograph is. The job of a spectrograph is to break up what we see as white light into wavelengths so it can be analyzed. And then it bounces back up to the viewing table. And we'll be looking at sunspots in here, but I'll show you the slit in the snow. These are sunspots, and Steve will tell you about the sunspot cycle. We're at a real exciting time. We're at solar max, so we've got lots of sunspots and they're big. You'll see this in the snow, and later on, if you feel like it, you can come and read the historical highlights. But we're gonna go see a telescope.
Is there something like magnification power somewhere measuring how far it can go or can see?
You mean the light?
It's just in general, all these different telescopes.
Oh, well,
Some are
yeah.
more popular ones, but is there a limit to how far they can see? Or does that work?
Well, the bigger the scope, the more you can see. So that's why they're building all these huge telescopes now. Yeah. So the 100-inch could see things the 60-inch couldn't. The 150-foot solar could do things the 60-foot couldn't. Bigger is better in the world of astronomy. All right, my friends, come on in. I'll introduce you to
This
Steve.
is the most solar activity at present. Happens quasi-cyclically.
All right, I would like to introduce, excuse me, please come in, you want to see. This is Steve Padilla. He is the operator observer and has been for almost 49 years.
Wow, what is this? Welcome. Okay, so wherever you're at, you might want to move in as close as you can, because I'm going to talk mainly about what's going on with the sun now, since we can see quite a number of sunspots. Now, we're now in a time period that we call solar maximum. So we have an 11-year sunspot cycle. This cycle began in 2019. It's solar minimum. There's two photos that illustrate the cycle. Solar minimum back there on the large picture on the left, and solar maximum on the right. So 2019 solar minimum, we started this, it took a while for sunspots to emerge, and slowly over the years, the number of spots has increased to a high point. So last year and this year have been very active with many sunspots and solar activity such as solar flares and CMEs, coronal mass ejections. So these are all associated with sunspots. So basically a sunspot is a cooler area that's where there's a strong magnetic field. So the magnetic fields are very strong in this wherever you see a sunspot. And that cooling caused by the magnetic field makes that area appear darker against the brighter solar disk. There's a difference about in the temperature of the sunspot, about 6,000 degrees Fahrenheit and 10,000 degrees the solar disk. So typically in a sunspot you can see that there's a dark inner part that's called the umbra, and then the lighter shaded area is called the penumbra. And the magnetic field would be strongest where the umbra is the darkest part of the sunspot, where it's the most intense magnetic field. And spots tend to form in groups. So today we can see that there are several groups of spots. This is one sunspot group here, and this is an unstable group currently capable of producing medium-sized solar flares. None so far have been reported, but I've been looking up to see what that sunspot group is doing. Now over here there's a spot here with a small trailing spot, so that's another group. And then here, this is actually two separate groups. This spot here is by itself, but this chain of spots here forms another group. So now these spots are changing. First of all, the sun rotates, so their positions change. Each day we see the spot groups in a different spot as a position. There's about 13 degrees of rotation per day, and the sun makes a full rotation in about 27 days. And it takes a spot, if it first emerges on the eastern limb, and we track it all the way through to the time it reaches the opposite limb, that's almost 2-week time period. And of course, some sunspots can go around more than once. To kind of give you a better perspective of sizes of today's spots, what I'm going to do next is place a couple models here. So one for the planet Jupiter. This is how Jupiter would compare to the sun on this scale. And then we have a place for our little Earth, which is the size of this little BB, is our Earth. So put the Earth there. And you can see that compared to some of today's spots, those spots are larger than the Earth. In fact, some of the umbras are about as big. The darkest parts of these spots are as large as the Earth. Now, if you're wondering what's the largest sunspot that's ever been recorded, we have a photograph from way back in 1947. It still holds the record, but maybe one day we'll exceed it. So for this photograph that I'll lay out, it shows how large it actually appeared.
Wow.
So when you have large spots in any solar activity, solar flares, CMEs, can be much larger. So larger the size of the sunspot group, any solar flare activity would tend to be very large. In the case of that 1947, it did erupt with some large solar flares that did cause some effects on communications and navigation systems. The good thing that we lucked out and that the power grid wasn't impacted in causing any power outages of any significant size. But that's something that that's always a concern, because that could have major effects on our everyday way of life. The other thing, in 1947, we didn't yet have satellites yet. It was still 1957 before the first satellites were up in orbit. In our modern world today, of course, with our numerous satellites, those could be impacted and do get impacted by interfering with, and actually always that chance it could actually cause damage to satellites. So it's an important reason to know what the sun is doing. But mostly these days we can rely on our solar telescopes up in orbit and solar spacecraft that can monitor the sun continuously and get that information out quickly. Whereas in the old days, when this telescope had a part to play in determining what these sunspot groups, if they had the potential for solar flare activity, we could get some indication from the magnetic measurements that were done with our spectrograph. So the spectrograph was an important part of what we did for many years. Now we're not doing so much now, in fact very little in terms of science, because there isn't the research funding. That dried up about 12 years ago. Some of the equipment that's part of the spectrograph is no longer in working condition, unless we did a major upgrade and had funding to do that. So we're kind of limited in what can still be done with our solar telescope as far as any kind of science. And it's actually a combination of art and science in the one simple observation that's still possible given the circumstances of our telescope. So I'm going to show you, actually I have to get over to the table over here and pull out a sunspot drawing. Excuse me here. Now I don't have one for today because we're kind of having some work being done, some things that don't work. We have some volunteer engineers that are working on that problem. But this is a sunspot drawing from yesterday. And you see, you might recognize some of the same spots, but of course their positions have changed since the sun is rotating. But these drawings have been done since 1917, every clear day when possible. And in addition to drawing the spots, the paper's laid out here and everything registered and the spots are drawn, then the positions of the spots are obtained, and we write down in solar coordinates, solar latitude, longitude, and then through the use of the spectrograph, then magnetic measurements are obtained to determine the magnetic field strength and the direction of that magnetic field. So that's all information that's added to these drawings. And so over the long term, we've covered many 11-year sunspot cycles since 1917. So the long data set has been useful to solar researchers, even in this simple form and the limited information, because this is all done visually. Now, a more advanced method of measuring the sun's magnetic fields involved an instrument called a magnetograph. That's what this long white box is called, the magnetograph. There's some other parts here that are associated with it, including a computer system in the other room that actually dates from the early 1970s, but that went out about 12 years ago as well. But in the time period between the late 1960s up until 12 years ago, about the year 2013, our magnetograph operated. And working with the spectrograph, with the spectrum, we were able to measure complete magnetic fields over the entire sun. And what you see on that back wall are illustrations of the various types of data obtained: the magnetic data, magnetic maps, the magnetograms, illustrated on the top row. There's also what are called Dopplerograms, since we could obtain velocity data by using Doppler methods. The rotation of the sun is one form of motion going on, but over the course of the magnetic cycle, the 22-year magnetic cycle, we were seeing interesting patterns in that Doppler data, where was showing that there were zones of the solar plasma that migrate from high latitudes to lower latitudes closer to the solar equator over the course of the magnetic cycle. That was something that had not previously been studied very well, but in doing many years of obtaining those observations, that led to some new discoveries with this telescope in that area. But the magnetic cycle, 2 complete magnetic cycles were covered, enough so that the solar astronomers could write scientific papers to show how those magnetic cycles, how they had changed from one to the other, any differences in that many years of data. So that long-term project came to an end, as I say, in 2013. So we're just limited to the drawings and keeping the telescope going for our tours and other programs we have, educational purposes. Anyway, but I won't get into the spectrograph because I think you'll get more of a lesson on that with Patricia over at the SNO telescope. But just to wrap up, point out that over on the tool cabinet over here, there's a bust. That's of George Ellery Hale. And then over on the wall there's photographs of Albert Einstein when he visited here back in 1931. And then a small photo of Stephen Hawking here in the center there when he was here back in 1990 for a visit. And then you can see out the door there's the elevator bucket. Normally just go up there once or twice on weekends, because the telescope initially, the dome has to be open. The 2 solar mirrors have to be aimed and adjusted so you can get the sunlight to come down through the lens so we get our image here. And that just takes me a few minutes to do. And I come down and then can work here with the image. Now today's a little different because our volunteer engineers have been working up there all morning. They took a little break, but they're going to come back and continue and hopefully get things working again. Just the certain telescope motions that allow me to move the image around here. The other stuff will have to wait for future time. But for now, if they can get the telescope motions, then I'm all set to make a drawing again. So that's basically what's going on here.
All right, we are now going to go see the SNO Solar Telescope. All right. I'll talk to you after, Steve. Come on out.
I didn't have time to ask him. He said solar latitude, solar
No, I think it's,
Yeah, so same as on a regular globe, latitude and yeah, so he positions them on the sun, just the same way we do with the Earth. Yeah, and then he also does magnetic polarity readings, so those are his.
I mean, across the sky. Sure.
Patricia,
Yes.
he has a question I'm sure you can answer.
Maybe, who is it?
I was wondering if because the sun is moving across the sky, do they have to manually follow it?
No, telescopes track. The
Okay.
sun rotates.
Yeah.
Yeah, so the sun is rotating, but all telescopes track, and the way the tracking mechanism works is you have a mechanism in the case of the SNO, it's a flywheel. It rotates at the same rate as the Earth is rotating, but in the opposite direction. So in theory, those motions cancel each other out.
Yeah.
And then you can adjust that. Like we just adjusted the tracking on the snow, and now it's just so nice. All right, so we'll wait for. Okay, and you'll close the door. All right, thank you. Let's continue.
Innovations happening here, or were they making telescopes bigger, or was there
Yeah.
something being innovated here?
We do use the two night scopes sometimes. Groups come in for something called speckle interferometry. So they're measuring the distance between binary stars, but we are primarily an historic observatory. So we're not modernizing our telescopes.
And I guess I should say, at the time, were these big innovations?
Oh, huge.
Okay, they
Everything
weren't
on
just
this
making
mountain.
them bigger, they were
No,
innovations.
everything was a first, an innovation, a risk, and everything worked. So, these are our reservoirs for drinking water and water for the observatory. They normally the staff tests them and treats them daily. LA County is now having us put in an automatic chlorination system, so that's going on. We have propane. Notice no power lines. All the electrical lines are buried. They're now doing that in the Palisades. They started in my community even before the fires, and that is the way to go in the mountains and canyons. A lot of those fires are starting from transformers. But anyhow, the 60-foot, as we know, is not used as a solar scope, and it's not open today. But all they do is the USC students come, go up the stairs, they open the dome, they turn on the camera, and then later on they download data. And one day I said, well, what's the criteria? How do you get to do this? And they said, well, you got to have a car. So, all right. So, are you a volunteer or really?
Oh yeah, no, that's,
Steve and I have solar, so.
yeah. No, I'm fully aware of that. That's why I like to find something just about the year, things like that, but it's going to be voluntary money. Yeah, I heard. Got it good.
So, 8 lucky people get to sit down. The rest of you don't. Go on in. We have 8 chairs.
Maybe a theater, a video.
All right. So, welcome to the Snow Solar Telescope. Once again, it is called the Snow because we have named Helen Snow Paper. So, This scope came up on what was then had become Mount Wilson Toll Road. So when Hale founded Mount Wilson in 1904, he signed a 99-year lease with the Mount Wilson Toll Road. And the agreement was that the road would always be open to the public, and they were just hoping for more traffic up here and make money. And there used to be a hotel here and all sorts of things. And then in 2003, when that 99-year lease ran out, the Carnegie Institute signed another 99-year lease with the LA National Forest. So there is a chilling clause in it, and that clause is, should Carnegie drop the lease, then Mount Wilson would be required to remove every bit of what is up there. Now, Carnegie won't do that. Mount Wilson, no one can afford to do it, but that's just scary, so that'll never happen. Okay, this is our founder, George Ellery Hale. So, he was born in 1868, lived to be only 70, but in those 70 years, he changed the face of astronomy. When Hale founded Mount Wilson, he did something that had never been done before. Prior to Mount Wilson, observatories were strictly for what is called observational astronomy. They were looking through telescopes, they were drawing what they had seen. They knew phases, cycles, positions, and movements, and that was it. Hale founded Mount Wilson, as the first observatory ever that was dedicated to astrophysics. Now, at the turn of the 20th century, astrophysics was a new and evolving field in science. To do astrophysics, the main tool you use is called a spectrograph. The job of a spectrograph is to break up what we see as white or visible light into the various wavelengths, and then they can be analyzed. The main component in a spectrograph is a piece of metal called a diffraction grating. It has scored parallel lines very, very close together, and each of those lines has an angled V groove. So the entrance to a spectrograph, and you'll see it in here, is a stationary slit, but you can tilt your grating. And because of those V grooves, the light will hit it, refract differently, and you'll see the spectrum in different ways, and I can show you that as well. In addition, all 5 scopes, 3 solars and 2 nights, had built-in cameras for long exposures and dark rooms to develop in those days glass plates. It was a game changer. Hale had it all set up, all the astronomers came here. Consequently, truly, every significant discovery in solar, stellar, and planetary astronomy all made at Mount Wilson during the first half of the 20th century. So what happened here is truly unrivaled in the world of science because it was here. Most observatories have 1 big scope, maybe 2. Hale had 5. Each scope was the largest in the world when it was built, till he built the next larger scope. The 100-inch was eventually unseated by the 200-inch at Palomar. Hale was part of that initial design process. Unfortunately, he died in 1938, and I think it saw first light in 1948, so he wasn't there, but it does carry his name. And of course, now we're on to huge scopes. But anyhow, that's Hale. Hale? It's all about spectroscopy. So we see just the middle of the electromagnetic spectrum, what we call white or visible light. But the spectrograph opens up all those other wavelengths, and every wavelength tells you something different. This is what spectroscopy does. Absolutely everyday science now, all research scopes go out with spectrographs and cameras, whether they're Earth or space-based. 2 good examples are the Hubble and the Webb. But in Hale's day, this was a cutting-edge telescope. This was something no one had ever done. Now, once you start breaking up light into wavelengths, you're going to be looking at a different version of the periodic table. Here we have the periodic table of spectra. These are called emission lines. On the snow stage, you'll see dark absorption lines. Every element has its own light fingerprint. These lines can tell you speed, distance, density, temperature, everything you want to know, if things are moving towards us or away from us. So, and Hale did not develop this. This was already in the works. There are 3 types of spectra. You'll see 2 here today, but first, you're going to feast your ears on the sound of a 120-year-old DC relay moving a 120-year-old DC motor. These are historic telescopes. Mount Wilson does not modernize the scopes. If we do adaptations, say to outfit the 2 big scopes for viewing for the public, it is never at the integrity of the design, mechanical or design integrity of these scopes. This is the most original scope. So behind that grate are DC relays. They activate the DC motor. So I'm just moving something up top to move some light. So this is the relay. This is the motor. I'm real happy because it didn't work for 2 years. And that's the thing we couldn't be doing. We could easily go buy a new DC motor, but oh no. We just find someone to repair it or we swap it out. because there's stuff stashed everywhere. All right, so here we go. Now, you've all seen a continuous spectrum because you've seen a rainbow. This is a little piece of diffraction grating. There we go. All right, so when you get to a different angle that is a stopping place on a diffraction grating, it's called an order. This is 0 order. First order, look at the space, now look at the ceiling. Do you see how second order is stretched out? That's a function of those angled V grooves. So the more stretched out your spectrum is, the higher your order is, and that means you're getting more out of your spectrograph, more information. Steve does his magnetic readings in the 7th order. That's a really high order, because that's where he finds the iron lines, but he's getting a lot out of his spectrograph. So, continuous spectrum. Okay. The second type you'll see here, it'll be an absorption line spectrum. Absorption lines appear as dark lines, and they're formed because the light has gone through a cool gas cloud. In the case of the sun, the outer layer of the sun is cooler than the interior. So as the light exits the sun through that final coolest layer, the photons absorb energy, the electrons get excited, they move to a higher energy level in the atom. For the emission lines, it's just the opposite. The light goes through a warm gas cloud, the photons lose energy, electrons drop down. And that's a super simple explanation. Kirchhoff stated the laws of the spectra simply shown. We see emission lines moving towards the nucleus of the atom where the higher energy levels are. Absorptions moving to the outer shells or levels, that's where the higher energy is. We know the sun and all stars are made mostly of hydrogen and helium. That's in the core of the star. It's as much as 95 to 98% of the stars, just those two elements. The core of the star is where nuclear fusion occurs. Nuclear fusion gives them their heat, brilliance, and luminosity. Once that star uses up its core elements, it's just going to kick out and grab whatever it can find. When all the fuel is gone, different types of stars die differently, but eventually dying stars will be surrounded by a cloud of gas and dust called a nebula. Inside that nebula, new stars will form. Should you come look through our big telescopes, you'll see several nebula, and you'll see the dying star in the middle called a white dwarf, and that's kind of a fun thing to see. But that's that. Different stars, different spectra. So the first big discovery Hale made with this telescope was in 1905. You just saw sunspots. Hale discovered that they're about 4,000 degrees Fahrenheit cooler than the areas around them. He had a strong hypothesis they occurred because of magnetic fields, could not prove it in the snow. So 4 years later, in 1908, he built the 60-foot, as well as the 60-inch, used the 60-foot to prove that, yes, indeed, sunspots are caused by magnetic fields. No one even knew there were magnetic fields outside of Earth, so it was a double discovery. Galileo had seen and drawn sunspots as early as 1612, so they were discussed for hundreds of years, but no one knew why they occurred or how they were different. When Hale presented that discovery to those observational astronomers, suddenly they were on board. So what Hale did here was he facilitated a pretty quick transition from observational astronomy to astrophysics. So that's a big deal. All right, if you're looking at a sunspot in white light, this is not what you saw in the photograph. And you go to the green wavelength on your diffraction grating and you isolate the iron absorption lines, you will see what's called the Zeeman effect. The bulge means there is a magnetic field. The split tells you its strength. Steve then uses a special viewing device he has, and he splits that split, and that's how he reads the polarities. Did he talk about the 11-year sunspot cycle? Okay. Now, this telescope was not installed with the spectrograph in the pit as it is today. Right here, under this plastic, when Hale was about 19 or 20 at MIT, he was also working at the Harvard Observatory, and so he designed and fabricated what is called a spectroheliograph. He also worked on that at Kenwood after undergrad. Simply described, it's an above-ground spectrograph, but it had some very unique capabilities. It could isolate wavelengths. No one had ever done that before. So here we have a photo taken with this telescope in 1906 with the spectroheliograph. We see sunspots, we know they're cooler. This white is called flocculi. It is a surface feature that was known already, but no one had photographed it. Just as sunspots show us cooler areas on the surface of the sun in the magnetic fields, flocculi show you hotter areas, and they do tend to occur near magnetic fields, so you always see a bunch near sunspots. He's also isolated H alpha, that's a red wavelength. Film emulsions were never red sensitive, so one of the many things Hale did was work with Kodak to develop a film emulsion that was red sensitive. He also had a little slit scan. so he could produce full surface images of the sun, just right across the whole disk. In 1849, two French physicists had fully imaged the sun with a daguerreotype photographic process, but not really since. So these were wild innovations, and once again, the astronomy community could now see features they had only read about. So I can't stress enough, everything Hale did up here was a first, it was an innovation, and it was amazing. It was 1904, 1910, you know, nuts. So there were some women who were really important during all of this, and one of them is Henrietta Swan Leavitt. She was one of the Harvard computers, so her job was to analyze the glass photographic plates made in the telescopes. She discovered a type of star called a Cepheid variable. There's a relatively short period of time where Cepheid variables get brighter and dimmer. She examined that relationship between the time and the luminosity, came up with a mathematical formula to measure distance. Suddenly they could measure millions of light years, not just hundreds of thousands. Scientists called her formula the yardstick to the universe. Without her work, the discoveries I'll tell you about in two big scopes could not have happened. She worked on site here in 1925, and that truly rare is the correct word. It was rare for any women to work up here as scientists in those early days. There were truly only a handful. And she proved in her dissertation, casually using quantum mechanics, that all stars are made mostly of hydrogen and helium. These women paved the way, I'm not going to say for bigger discoveries, for discoveries that became very famous. So without their work, it would have been a much longer road. Now, the way the telescope works, okay, for a special treat.
Yay!
We'll go upstairs and just stand on the bridge and look at the mirrors, but I'll describe it before
I
we
thought
go.
you were going to say champagne.
Too early. So we have the coelostat mirrors up here. Now they're the same as Steve's in the 150 foot. His are smaller because he's got that objective lens and his top flat points down, but this is horizontal. So we have two mirrors, they're called a coelostat, both flat surface. The bottom mirror pivots to track the top relative to the rate of rotation of the Earth. We call it a clock drive because it's very similar to a grandfather clock mechanism. There's a brass flywheel that is gravity driven by a cable and a weight. It engages a single gear. I slide in the solar ratio gear set because you can use this scope at night for the moon and bright stars, and we're good to go. So, light in the bottom up to the top. Top sends it 100 feet behind us to the primary mirror. The primary has a slight concave curve. The light is focused there. Beam of light up to the tilting mirror. Tilting mirror sends it through this slit. So this is the entrance to the spectrograph. Same on the 150 foot, barely open. Before the light hits that diffraction grating, it's going to travel 18 feet, and there's a lens right above the grating. It's called the littrospectrograph after Mr. Littrow. And the lens, the job of the lens is to collimate or align the light. So it hits the grating properly. The wavelengths are broken up into wavelengths, absorption lines are formed, bounces off the grating, is refocused by the lens, and after we look up there, you can come here, and if you stand here, put your hands here, and just look, you'll see part of the solar spectrum, and you'll see some absorption lines to the left and right. The two very prominent lines in the center are the sodium D lines. For all my friends under 18, you've been such good listeners, and I know kids don't always like tours, please come and pick 2 cards of objects of your choice, and you can read about them on the back. I like to call them science Pokemon cards. Okay, adults, follow me. Take a look at the mirrors and then we'll we're not that far up, we're only 3 feet. All right, yeah, we should be careful, all right? Okay, so. I don't usually bring the tour up, but when I like the group, I take it. So I like you guys. All right, so this is a roll-off shell. And that tends to be more of an amateur telescope configuration. See the crank at the end? So I roll the shed back to reveal the mirrors, and then when I close after the tour, I'll just roll it forward. Okay. The celestat mirrors, the position between the mirrors is completely reliant on time of year. So I chuckled yesterday, I was at my summer position, and now I'm moving back towards my winter position, which will be mirrors right on top of each other. This telescope is great for understanding the seasons and how the sun and the earth are related and how they move. But anyhow, so this time of year is also a glorious time of year because I can stay parked in the middle all day because the sun is high. The rest of the seasons I start in the east in the morning, about 12:30 to 1:30, the second or top flat shadows the bottom one. That's probably when Hale had lunch because you just can't avoid it. And after 1:30 I move to the west. So this is, you get the flywheels in here. This is the tracking arm. If you ever doubted, and I know you didn't, that the earth rotates, there's your proof. There's the cable with the weight. There used to be a viewing device on this. It's gone, which is a shame because that's how you find stars at night. Otherwise, forget it. And it's all original, so it's just a beautiful telescope. It's a really unique configuration. This is the world's oldest permanently installed working solar telescope open to the public. There's one 4 years older in India, but it's not open to the public. And then there's one other of this design in Japan at the University of Kyoto. So it's an extremely unusual telescope. It was never open to the public. I started opening it 3 summers ago, and now it's part of all the tours and the engineers' tours. And I felt very strongly that the public needed to see it because it's just a cool telescope.
On most telescopes nowadays, the not reflective, but refractive.
No, more reflectors, because reflectors give you more light. On refracting telescopes, the reason we changed, or Hale changed to reflectors up here is when you do spectroscopy, you're dealing with colored wavelengths. Refracting telescopes, because of the lenses, have something called chromatic aberration, where basically color is introduced, and that would make spectroscopy hard to do. So, but when Hale was at Yerkes, when he founded Yerkes at 24, soon after, he and Richie, his chief designer, they did the 40-inch and they were getting amazing results, but they designed a little 24-inch proof of concept prototype reflector telescope, and the results far exceeded the 40-inch. That was when he knew what he was going to do here. Although that was in 1896, his dad bought him the 60-inch glass blank for the 60-inch telescope. Telescope wasn't designed. Observatory wasn't founded till 1904. Yet another example of how far ahead Hale planned. It's really amazing. So I hope I'm putting all the puzzle pieces together for you well, because that to me is something so amazing about him. Okay, so now we're going to go carefully downstairs and look at the solar spectrum, and then we're going to go see the 2 big scopes. How many what? It's an hour and a half till it resets, and I think it's 27 hours to go a full rotation. Yeah, so it just resets every hour and a half if the motor works. Otherwise, I run up here every hour and a half. Luckily, we fixed it. We have some amazing new technical. Oh, don't do that this one. Okay, hold on. Yeah.
Would the tree be in the way?
The tree is it? That tree's not in the way, but the trees to the side are in the way.
Yeah.
Those trees were not here when Hale built this. Yep, they are.
You want me to hold the bottle?
So check out the spectrum. That's pretty.
Every mirror you have, do you have to have 2 mirrors? The first mirror would be your opposite, right?
Well, and she's bouncing light, so it's just sun, bounce, bounce, bounce down.
I don't think that you have 2.
We have, yeah, but they're just one mirror feeds the next mirror. Yeah, so we have 4. And then after you look, go ahead and go out the door just for traffic. Did my student friends get their cards?
I don't know. Yes.
Be sure you do. All right.
Thanks for taking us there. That's really cool.
Oh, yeah, it is.
Thank you.
All right. Make sure you see it so it's on that glass. Right here.
No,
stuff.
You gotta look at that. In the spectrum.
So here it is.
So what are we looking at?
You're looking at the solar spectrum and some absorption lines.
Oh.
Do you see the colors in the lines?
Yeah.
Yeah.
That's the magic. Feel free, you can touch it, it won't break. Yeah, that's all you. So that's the actual, I just approved something, see, it disappears.
We are not done yet.
You are barely started. I'll go.
Do you see?
Oh, I do, I'm trying to figure out how much I need to cut in this area.
So here's the solar spectrum. See, well, tell me what you see.
What do you see?
Yeah.
Different colors, right?
Another word for a rainbow is a spectrum. That's the scientific word. So what happens is when light from the sun looks white to us, this is really all the colors that make it up. Because when you mix all the colors together, you get white. Mm-hmm. All right. Okay, we're going to continue.
Like it's actually a bunch of different colors.
No guess. Man, I owe you this. I owe you $1.
So boring or so boring? I think the whole those fucking things, that's not boring.
Setting up for it today.
Well, you don't know what we're going to figure it out.
Oh, wow. Like nothing else. Yeah, once you start feeling woozy up here, it's kind of hard to get. It's over 100 years old, and at night I look out at the city lights of LA. Sometimes
Can you see stars?
I can see amazing stars. Sometimes I can see the Milky Way.
Wow, that's nice.
And sometimes a bear came in my driveway one time. Yeah.
Is that why there are is there a bear area?
Yes, but we rarely see them. You know, they're pretty good. They didn't want to hang around with us. They want to go find food. So you notice there's no trash cans here? That's because of the bears. So that keeps the bears from getting in trouble. When bears are around people, sometimes it doesn't work out. It's not the bears' fault. Sometimes people feed them, and then the bears get too familiar with people, and then I'm like, got nothing on. But yes, it's beautiful. I'm tired. I know, sweetie. It's a long walk. Great, though. You got your cards? Yeah. Okay, good. All right.
Okay.
Somewhere up here even.
So just very quickly before we go in, the spectrograph in the big scope, see that kind of triangular protrusion? It's housed just barely underground. The spectrographs in solar pits are in the pits. It helps establish focal length as well as image size. Okay, but let's go inside because that's way more fun. And will the last person, Michael, thank you. Michael will get the door. And it'll be cool in here. All right. We're going up. Some lights too. All right, up we go.
we have a tour.
We're gonna do sort of about inside what we got.
We're gonna watch her.
Let her tour go in and we'll scale this up.
Okay. I'm going to make a health comment. I haven't seen anyone drink any water. Some of you may have been. Please, 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 if you're not drinking water on the tour, please drink a lot of water when you get down to your cars, because it's just easy to get dehydrated up here. Okay, so welcome to the 60-inch telescope. These night scopes are named by the diameter of their primary mirrors, which is here. So the optical design in the 60-inch and the 100-inch are the same, but the yokes are different, and that's strictly a matter of weight. So the primary mirrors here, secondary mirror there, tertiary in here. This mirror weighs just 1,900 pounds, and you'll know why I said that when you go to the 100-inch. This telescope weighs 22.7 tons, and it has an amazing design feature. So both the 60-inch and the 100-inch. The 100-inch weighs 100 tons. Its mirror weighs 1,800 pounds. These scopes are original bearings because there's a very clever design element. These scopes float on Mercury. This was a lighthouse technology that other telescope makers tried to employ unsuccessfully. Ritchie and Hale didn't know the meaning of not successful, so they made it work. That Mercury is very shallow, maybe 8 inches deep, carries 90% of the weight of the telescope. That's amazing. Other little odd things, they got hold of some sort of military suits, and you could plug yourself into the DC power, to keep warm. So this shutter opens like this, and then both the big domes rotate. Steve's the two tall solar towers rotate as well. So you open your dome, and then you rotate to the part of the sky you want to see something. Now, many discoveries were made on this telescope, but the most famous were done by a scientist named Carlo Shapley. Object called a globular cluster. So, these are globular clusters. There are two types of globular clusters. There are open clusters like the Pleiades, with stars, and then there are these globular clusters, my favorite object because it's what space looks like, that have hundreds of thousands of stars. So Shapley was, at the time Shapley was doing this research, the general belief was that our solar system must certainly be in the middle of the Milky Way galaxy, because, you know, it's all about us. And also that the diameter of the Milky Way galaxy was not known. So Shapley was under the impression that all globular clusters were the same brightness and the same distance. So here is a globular cluster. Yes, indeed. So Shapley's observing globular clusters, and he's taking measurements from Cepheid variable stars using Henrietta Swan-Leavitt's formula, and he very quickly discovered that no, they're not all the same distance, and no, they're not all the same brightness. Based on his measurements, he discovered two things. He discovered that we're out here. I can't tilt it or the globular cluster will fall, but we're out in the third of the Milky Way. And he determined that the diameter of the Milky Way galaxy was 330,000 light years. Now that was incorrect, and that was not discovered until sometime later. What happened was...
He was measuring the distance to the globular clusters with the redshift?
The redshift came later, so he was just measuring, because Walter Baade discovered redshift, blue shift in the No, that was Vesso Schleifer, I'm sorry, a German astronomer. So he was using Henrietta Swan-Leavitt's formula for distance. Redshift, blue shift came in the 100-inch with Hubble. But, so he thought it was 330,000 light years, and it wasn't until many years later, a scientist named Walter Baade, a German scientist who was here when the war started, working on the telescopes, and the US government called him some horrible designation like, hostile alien or something, and he had to leave, but the observatory said, he's a scientist, let him stay, we'll watch him. So he had the observatory pretty much to himself. They had a lot of blackouts in Pasadena, so this was great. And Walter Baade discovered in the 100-inch a second type of Cepheid variable star that required a different formula. It turned out that Shapley had misidentified that Cepheid variable because the second type hadn't been discovered yet. So when they plugged in Walter Bade's new formula for the second type of Cepheid variable, then we discovered that the actual diameter of the Milky Way galaxy is about 110,000 years. This was a huge relief to many people because with the 330,000 light year measurement, like the oldest star was younger than the universe or something, so it's a big problem. But that was all cleared up. So now we know 110,000 light years, we're over here. These telescopes can be used three ways. So they can be used as cameras, and that was called the Cassegrain focus, and we did, so this is where the film plate would go. And we actually got a hold of some glass plates a few years ago and photographed the moon, and then we went downstairs in the darkroom and developed it. And it was just an homage to Hale, but it was really, really fun. So this is where you took photos. This is where you view. So we put a lens in here, and then sometimes you climb up to the top of that ladder and almost climb on the telescope. I encourage you to go to our website. So many opportunities to view through the telescopes. It's worth it. Second configuration was the Coudet spectroscope. Coudet means elbow in French, and that was for doing spectroscopic work. And then the third way to use it was a Newtonian cage way up there. That's where they viewed eye to glass. So that's this platform goes up on rails, and then you'd be way up there viewing in the freezing cold all night long. The way they did the photographs was, say they started, so they're like 4x5 cameras or 8x10s, these were 4x5s. You remove a metal slide to expose the plate to the light. Say it gets cloudy or you're tired, you just slide it back in so no more light hits the plate, go rest, come back, and then they had to get realigned. So they always chose a guide star, and they would line up the crosshairs. Now there was a story that there was a certain mule who had the best tail hair in the town. And that mule was the one who made crosshairs for the viewing. And that mule didn't have to haul heavy things anymore. I thought that was a made-up story, but I actually have a photo of that crosshair, so it's real. Another story is that they use spider webs. Not so sure. But the mule hair is true. We run on DC power, so that's behind you. And any questions? You guys are free to walk around.
What if the globular clusters were galaxies, or what were they?
They're just big groups of stars. Hundreds of thousands, they're the oldest stars out there.
Also, the only axis is this way, is that correct?
No, you have, in telescopes, you have declination, which is north-south, and right azimuth, which is east-west. So we can pitch that way and we can rotate. Yes?
So when do you open the dome?
This is JT and his friends. JT has joined us in the last year, and he is stepping in the shoes of our 97-year-old chief engineer, so JT is in we are a volunteer, as I say, Mount Wilson runs on the passion of its volunteers. That is very true, so anyhow, well, we have a new volunteer as well. Carl. Yay, Carl! Alright, so you guys can come around, you can take photos. If you'd like a photo of you with the telescope, I'm happy to take it. And when you're ready, we'll head off to our last scope. Okay? Alright. Over down there. I'll say it.
So the one is the mount. These mounts points directly.
closer. I know. Look up.
He's gonna open it.
And this stuff's really noisy, the 100 inches much quieter. Well, okay, so that friends and family. My friends, I think we're going to go ahead and move on. So if you go downstairs and wait for me outside.
Yeah. You know, you take the tube out, the water stay inside.
Yeah, it's
Like, ready to.
We're headed off to our last telescope. Oh, okay, yeah, that's a prism. It's called Sun Star, I think. It's just a prism up there. And it's too late in the day. We have a spectrum projected here, actually.
Can I see it right
Yeah, it's just faintly still there. So if you do this and you look, you can get most of the colors of the spectrum. That's just for fun. Yeah. All right.
It's a big one.
Oh.
So she said that her before we started the tour, and then we started. I got some Russian with it.
So.
It's all like Darrow.
All right.
Pretty fantastic. Yeah.
He used to aim it, our director controls it with his laptop from home, but he used to aim it like at events in town, but then one day Steve and I were, one evening we were walking and we just saw random spectra around, so then we decided to keep it up here, which I think is more fun. We have stopped here because this is one of the Chara domes, so that, once again, Center for High Angular Resolution Astronomy. Interferometry, there's a whole signboard that can explain it far better than I, but what they have is they have 3 pairs of telescopes scattered around the observatory grounds. On any given night, all 6 scopes are looking at the same object and gathering light, and then see these metal tubes? Those are vacuum tubes. They transmit the light to the Chara laboratory, which is behind the 100-inch. What interferometry does is it uses smaller mirrors spaced wide apart to simulate one gigantic mirror, because it's all about gathering light. So this is super state-of-the-art stuff, highest resolution interferometry in the world, we're told. That little dome is new. That's their little portable 7th dome. So that'll be moved around the grounds depending on what's to look at. So this is the Chara array part of it, and that'll tell you more about it for later. All right, we're going to go to our last telescope. You want to go back in?
I don't know how the Airbnb will work, but I imagine because by itself is no other thing. It looks like you're just looking at a mountain and there's a house.
All right. So we are paused here because you are about to walk in Einstein's footsteps and Hawking's wheel tracks. This is the bridge to the 100-inch. That big reservoir on our right was put in by the County of LA after the 2009 station fire. It is 530,000 gallons. It was full when the Bobcat started. So you notice we're super well cleared. Our main crew of about 3 guys, they stayed here until the firefighters said, you can leave or we'll helicopter you out. But by the time they left, the firefighters knew every inch of this place. This saved us, and it saves us every time. We also get saved all those communication towers at the entrance to the observatory. That's big bucks. They will go to any lengths to save those, so we kind of fall under that umbrella, which is great. But we've survived always. Mountains, canyons, you're always going to have fires. Okay. Pausing here to look at that. So, as you walk by, this is a Newtonian cage from this telescope. It was in the Smithsonian for 27 years. It came back to us in June of 2023. That is Edwin Hubble, way up top, observing, but that shows you the camera plate, and it's just very beautiful. Okay. Oh, you guys have a seat? Lucas, have a seat? So, all right. So, you may hear this referred to as the Hooker telescope. A man named John Hooker paid for the glass for the primary mirror. It was $45,000. But this telescope, a lot of work was done on it, many discoveries, but it's most famous for the work, the discovery made by Edwin Hubble. There are many stories about Hubble, but I think one of the things I find very interesting about him is that he was more of an observational astronomer than an astrophysicist, although he really did make one of the biggest discoveries ever made. So, Hubble was observing on October 6, 1923. He spotted a star that he thought was a nova. Nova stars get brighter and dimmer, but over a very long period of time. But he went back and photographed it, and he started looking and comparing the glass plates, and he realized it's not a nova, it's a, crossed out in red, variable star. He had found a second variable. He was very excited for the red. And so he, using Henrietta Swan Leavitt's formula, he made a measurement, and he discovered that what he thought was a nebula was actually outside the known diameter of the Milky Way, and it was a galaxy. Hubble discovered Andromeda. Now, there was another scientist, Vessel Slipher, who came up with the formula to determine redshift. Is it moving away from us, or blue shift moving towards us? Andromeda is the only thing out there moving towards us, and it'll be bazillions of years before it hits us, so none of us have to worry. But this was a huge discovery, and then he started looking more and more, and he was discovering more and more galaxies, and he was discovering that the further away from us they were, the faster they were moving away from us. This was huge. So when you hear that Hubble discovered the universe in the 100-inch at Mount Wilson, or Hubble discovered the expansion of the universe in the 100-inch at Mount Wilson, that is what they're talking about. Now, the story of this telescope, the glass plane for this telescope that the primary mirror is made from arrived in Pasadena on the same night that the 60-inch saw first light, meaning the first time it was worked. Another example of how far ahead Hale planned. He didn't know for sure if the 60-inch would work. He was pretty certain because they had done that 24-inch prototype proof of concept at Yerkes, but he was confident enough that he had someone invest $45,000 to get this second piece of glass. So over and over, Hale was always one or two telescopes ahead. So this glass, the glass for this scope, this is actually 101 inches in diameter, and the 60 inch is 60. They were both poured at a foundry in France called San Gabriel. The reason it was poured there is there simply was no foundry in this country that could pour such big pieces of glass. They did 3 pours, and they sent it over to Santa Barbara Street. Hale and Ritchie went to look at it, and they said, well, this won't work. It has bubbles. We can see layers. They thought it was a nightmare and a disaster. Lots of drama, trips back and forth. And they did several more pours. None of them were any better. So Ritchie and Hale went back and said, let's give it a try. Let's start to grind it and polish it and see what happens. It turned out it was just fine. The bubbles didn't weaken in. They didn't open up holes. So it worked out. So then they coated it with silver, as they did in those days, and it was time to use the telescope. So there was quite a few people here. It was a big event. And this was famous all over the world. And they opened up the telescope, and they looked through it, and there was a bright object, possibly Venus, but it wasn't just one. It was several. They were overlapped. They were out of focus. Their worst nightmare had come true. As they started to panic, they kind of reeled themselves in, and they went through the course of the day, and they realized the workers had the dome open. So when you have a piece of glass that's, I think, 13.5 inches at the edges, 12 inches in the middle, it weighs 8,900 pounds, it heated up, and it was silver coated. So it had heated up and it distorted the surface. So they kind of relaxed, they went back to the monastery, rested for a while, came back, that object was gone, but they found a star, perfect. So it worked. Now, this scope, the glass weighs 8,900 pounds, the entire scope weighs 100 tons, the dome weighs 500 tons. Same optical configuration, we have the primary, the secondary up there, tertiary, we have the spectrograph, we have, we can use it as a camera, and way up there is where you view. After the tour is over, I encourage you just open, if you just don't do anything more than open the door to the char exhibit across from us, you'll see this giant I-beam. Think of that as the first interferometer by Albert Michelson. Think of that on top of this scope. The guy at each end just in there is one in the middle. It's pretty mind-blowing. This rises mercury as well, just absorbing most of the load, and it's double yoked because of the weight. So we're yoked over here, and we're yoked over there. The 60-inch can go to true polar north, although our director of telescope said I never go there. It's frightening to see how the telescope kind of has to get there. This one has limitations because of the yoke design, but each telescope sees it differently. Bigger telescopes, that's the trend. We're going to look at the glass, and then, the other thing is, these are not go-to telescopes, so the operators don't just type in go-to Saturn and the telescope goes. They need to know know what's in the sky at what time of year, what time of night. They run the coordinates and then they manually jog the telescope. We have something called a TELRAD, which is an eye viewing device so that if something happens and you don't know where you are, it sort of happens as I've been here, you can actually look inside it. So we're going to look at the glass in this telescope. You'll be able to see the bubbles, the layers. It looks green because it's just very thick, regular old plate glass. And then you can wander around, take photos, and then that'll be it. All right, let's take a look at the glass. So you can come and look. Wait, I have so you'll see the bubbles. Okay, so that's just the hardware. It is amazing. And there's the bubbles. So you can see why they were fearful that they would be problematic, but they weren't. But I mean, just look at the nuts and bolts. It's amazing. That's all right. Sorry. Don't worry. Okay. Oh, you're fine.
Oh, wow.
Lucas, can you see? Can you go in front of me?
The glass?
Yeah, it's glass. Bubbles in the glass.
And it's 13 inches thick.
13 and a half at the edges, 12 in the middle because it's a parabola.
We're looking at the edges.
We're looking at the bottom. So we're looking at the bottom of the mirror, and then it's just a recipient for the reflective surface, and also to define the lens shape or the mirror shape.
So the bubble makes it imperfection, right?
Yeah, but it turned out it didn't, you know, cause a problem. Because remember, this is just to give the shape so that it's a parabola and also something to coat with the silver and now aluminum. So it's just receives the reflective. Yeah, super thick.
With now today's technology, you can pour a glass without a bubble by having it constantly shaking it, right?
Yeah, and they also
Vibration.
wouldn't. Yeah, they would use quartz or Pyrex or something different. They wouldn't use. This is old-fashioned glass.
Do they have viewing here at night or something?
Yeah, lots of opportunities to view. Definitely go to our website and check it out because it's worth the trip.
So does the website have video of what this shows?
I don't think it has any videos. You could probably find some on YouTube, but the website will tell you events and all the different things that go on, and you can rent out a telescope with your friends for a half night.
That's cool.
Which is not okay. Did everyone see? All right.
Thank you for the great tour.
You are most welcome. It was my pleasure.
Bye. Have a nice day.
Goodbye. Bye, Lucas.
Bye-bye.